Good afternoon, everyone. Welcome to our class again, and we continue our discussion on multiple linear regression. Last time, we began discussing the purpose of creating a model, a multiple linear regression model. We said that uh, a multiple linear regression model is used in order to determine a relationship or associationship between a variable of interest and its relation to some other variables. So we'd like to not only establish a relationship or see a relationship if there's any, but also we'd like to see or be able to predict your variable of interest, your dependent variable, making use of your dependent variables. So we said that a multiple linear regression, MLR shortcut, it's a statistical technique that where we use several explanatory variables or IVs in order to predict an outcome variable, a response variable called your DV. Okay, the goal is to create a model so that we can explain your DV using your IVs, or we want to predict your dependent variable. Okay, so I showed this to you last time. I think, if I'm not mistaken, I think this ran last time, but I'm having problems now with my LaTeX. I don't know why it's not printing. Okay. Anyway, so this is just the equation. This is your y sub I. Okay. It's equal to your intercept plus your slope beta 1 multiplied by your independent variable x1, your beta 2 multiplied by your independent variable x2, beta 3 multiplied by independent variable x3 up to the number of predictors n, and predictors times your independent variable x sub n, plus a certain error term, residual. Okay, and then we describe what these are. Your y is your dependent variable, your x's are your explanatory variables, beta 0 is your constant term intercept, beta n refer to the slopes of each of your independent variable, and epsilon is your residuals or error terms. Okay. Now we said that there are important assumptions in creating a multiple linear regression model. The first is linearity of the data. What do we mean by this? Your dependent variable and your independent variable, if you plot them into a scatter plot, they should be related, okay, linearly. So we illustrated that last term. If I plot my y variable, my dependent variable on the y axis, and then my independent variable on the x-axis, and we create a scatter plot out of that, okay, there should be a semblance of a linear relationship, just like this. So the propensity of the data seems to be, as x increases, y also increases. Seems to be like this, okay? There is a linear relationship. If it was like this, if the plot behaved this way, then it doesn't seem like a linear relationship. There seems to be a wave-like structure like this. Okay? So if your relationship, if the relationship between your dependent and your independent looks like this, then this might not, this is best not modeled using a linear regression model. Perhaps another function, like maybe a sinusoidal function, okay, a polynomial function, but not a linear model. So that's what we meant by linearity of the data. Okay, if it was like this, something like this, then like just like a parabola, then this would have been a quadratic model or a polynomial model. Okay, so the y and the x, the dependent and the independent variables should have a linear relationship. Okay, otherwise it doesn't make any sense to make use of a regression model if your x and your y are not related linearly. Second, okay, second is that assumption two, linearity as far as the parameters is concerned. Okay, so what do we mean by linearity in the parameters? Here you have our LaTeX equation. Let me just rewrite that. Your y sub I is equal to, this is your intercept beta null, plus this is your slope for your x sub 1, that's beta 1 times x1. Okay. Wait, I'm not reading the right. I should go up here. Reclass. So I'll just read it. This is y sub I. This is equal to beta null. This is beta 1. Take note, your beta 1 here is squared. If I write this, y sub I is equal to beta null plus beta 1 squared x sub 1, okay, plus beta 2 x sub 2, okay. It's only beta 1 that's squared here. That's a caret 2 squared up to beta sub n x sub n plus a certain error term. Now, the parameters, the betas, beta 1, beta 2, beta 3, etc., should be linear. What do we mean by linear? Your beta should not be squared or cubed. It should not be raised to a certain power. Okay, it should not be like this, raised to 1/2, for example, beta 1. It should not be e raised to the beta, okay, or 1 over beta, okay, because if your parameters are modeled this way, then they're not linear, okay, and your a multiple linear regression would be, it would be difficult to solve your betas, your parameters, if your model is structured that way. So when we say linearity in parameters, it should be that your betas, your parameters, beta 1, beta 2, etc., should not contain any power, should not contain any exponent. Okay. However, okay, this does not preclude us from changing your independent variables, okay, your predictors. Okay, so if you take a look at this, y sub I is equal to beta null plus beta 1 times x squared. All right, so in that case, this is okay. Y sub I is equal to beta null plus beta 1 x squared, okay, plus beta 2 log of x, okay, plus beta 3 times 1 over x sub 3, okay, or x to the negative 1, okay. So these are okay. In fact, we can have also beta 4 times x1 times x2. This is called interaction. You can interact two independent variables. So in this case, it's okay to solve this using multiple linear regression. Okay. Notice the difference between the first one. Here, the betas are linear. That's okay. Here, the x's, the independent variables, may not be linear. Here, it's squared. Here, it's log. Here, it's to the power negative 1. Okay. Here, you have an interaction between x1 and x2. Okay. So this is okay. If your predictors are the ones that are, let's say, expressed as a function of, uh, let's say, squared or cube or square root, that is okay. Okay, that is perfectly fine, but not the betas. All right. So those are the first two, linear relationship between the independent variable and the independent variable. We also have linearity in the parameters. So let me pause for a while and seek your feedback if we're okay so far. Thank you. How about the others, please? Okay, good. Thank you so much. Okay, appreciate your feedback, class. That's very important for me. Okay, and as you know, in this class, this is a journey that we take, and we're all co-learners here. We would not, as much as possible, we would not want to leave anyone behind. Okay, third assumption, residuals. Okay, I already mentioned residuals a while ago, but let's elaborate on that. Okay, let me explain it this way. Okay, so maybe it's best for us to let's load first. Let's go here below. I'd like to make use of the wage data set here. Import data set. I'm not seeing. Yeah, sorry. Let me open this one. Wait. Plus, sorry, let me close this first. And I'm going to open cancel. I'm going to open the our project that we were working on. It seems that I'm not inside an R project, so this is not good. Always work inside an R project. You can see that there's no indication of an R project here. So let me close this first. And okay, let me open now my R project. Sorry, it's taking quite some time. Okay, good. So double check there. It's best to work with your inside your R project. Okay, so let's go here first, class. Let's please go to that line, create wage one object. Not this one here. Import wage. Can you see that, please? Kindly chat if you are able to see this line, import wage. Again, it's best really to if I had placed here import wage, then it would have been easy to look for that. Because even if there are so many code chunks here, it would have been easy to find that chunk, import wage. All right, do you have it now? Plus, kindly chat, please, if you were able to see it. And I'll just discuss with you how we can access the file that, okay, good, file that I shared with you. Again, class, when you comment, please make sure that you comment to the whole class. Okay, how about the others? Okay, waiting for the others to give the response. All right, thank you. Okay, so I think before we note one, what do you mean note one? No import on your end. Wala ba? How about the others, please? Pero yung iba, bakit? Why can't they see it? $96 lines. Okay. So it's not here. Okay. If it's not there, file. Wait, let me see. Let me first look at the folder. Ah, yes. Okay. Was this the only file that I gave you? All right. I'm sorry about that. Okay. So I think, yeah, I haven't shared with the complete one. Okay. Let's just do that. Let's just write first. Okay. May I request you to please write? Just go anywhere in your RMD file and then just type this one and then create this code chunk. You know how to create a code chunk. And then wage, then read underscore CSV, and then wage.csv, column names is equal to true. Kindly write that code, please. And then let's see what happens. Just make sure that you're inside your R project, and then you have already loaded the wage data set. Okay. Don't run it first. We'll run it all together. So if you're already done, kindly please chat yes, so that I know when to proceed. Okay, normally this one I would not give the code to you. I would ask you to write it. So uh so kindly write it, and you may want to give a name to your R, your code chunk. And when you're done, kindly please chat yes. Okay, thank you. Thank you. Okay, good. Now let's see, class. Take a look at this code. We're creating an object called wage. Okay, you can of course name it any way you want. You can name it data or whatever. here I just use this a name called wage. And then remember this assignment operator. Okay. What's a shortcut for the assignment operator class? This one. So that you don't have to type it. What's the shortcut for this one? I discussed this last time with you. Yeah, thank you, Marga. It's Alt minus. For Mac, I think it's Option minus. Okay, Alt minus, and then read underscore CSV, open parenthesis, wage dot CSV under quotes, and then comma, column underscore names is equal to true. Okay, now this function allows us to read a particular CSV file. Okay, you have the CSV file. Make sure your CSV file is inside your R project, because otherwise you cannot, if it's not here in the R project itself, then you will have to write just like this, the exact file location. Let's say C, desktop, etc. You'll have to write the exact location where that file is. That's why it's very convenient, class, to collect all your files inside that R project, so that when you access it, it will just be wage.csv, just the name of the file, and you don't have to use the file location, because since we're in that working directory, then you don't have to identify where this is located. All right. Could you tell me what happens if you run this, class? Were you able to run it? What was the message? What was the message, class? You may copy it, please, and then put it in the chat box. Hello, class. Did it load? Did this data load? What's taking so long, class? Okay, error. Thank you, Lisa. Error in could not find function CSV. Okay, error. Okay, also kay J. Others also? All right, good. So we purposely did that, class, so that you understand that you just can't use any function. This is a function. This is a command. If the package has not been installed. So first things first, let's take a look at your packages here. And please type tidyverse, tidyverse. Okay. Kindly type tidyverse and tell me if you see tidyverse here under your packages. Yes or no, please, if you can see tidyverse. Yes, yes, yes. How about the others? Okay. May I ask you, class, did we learn how to install packages last time? Did we talk about installing packages? I'm sorry, I got confused maybe with the other section. Did we learn how to install packages last time? Did we discuss that function, install that packages? Plus, Hello. There seems to be a lag between the how quickly you answer, respond, and yeah, your responses. Did we discuss, class, the function install the packages and library and require? Hello, class. Okay, not yet. Okay, thank you. All right. So the reason why this is not running is because this read underscore CSV comes from a particular package, and that package is not yet loaded. It might it might have been installed but not yet loaded. So first, let's go. Let's first learn how to install a package. Control Alt I. Please create a code chunk. So let's just give this a name, packages. For now, we'll just learn how to install one package. All right, there are several ways to install a package. First is this one, install that packages. Okay, that's the command we can use. Install that packages, and let's install a package that will contain the function read underscore CSV, and that's tidyverse. Actually, tidyverse is a family of packages, which we'll show you in a while. It contains several packages. So remember, all functions in R, except for those that are in base R, can be accessed for our use by installing particular packages. And last time we showed that there are more than 21,000 packages. So to sit to suit whatever statistical function you might want to perform. So this is one way to install that packages. Without running this, another way is to go here, packages, and then click this install, and then type here tidyverse. There. Okay. So that's another one. I'll cancel this. Go to packages and then install. Or another one is go to tools. The first one here is install packages. You'll be you'll be brought to the same dialog box here. So type tidyverse. All right. All right. So either one of those, through tools, through packages install, you can install that particular package. Okay. Now let's use this. Install that package as tidyverse. So I'm going to run this. Either go here, Control Enter, or go here, click this one, run current chunk. Run current chunk means all the codes inside this code chunk will be run. Okay. So if you would only want to run a particular line inside the code chunk and not all of the codes inside there. So just go to that specific line anywhere there, at the end, at the beginning, in the middle, okay, anywhere there, and then control enter. Control enter, or in Mac it's command enter, I think. There you go. And then we have a message here. Okay, in my case, one or more packages to be updated are currently loaded. Resetting R prior to install is highly recommended. If you receive a message like this, class, it will be best for you to restart R. Okay, it will not take long. Okay, so in my case, I'm going to restart R. So kindly wait. In your case, if not, then just proceed with the installation of tidyverse. Yes. All right. Now the problem is this might keep on repeating because okay, starting R. Okay. All right. Then again, last time, if this still requires me to restart, I'll cancel it first. Okay. No, just click no. All right. So if you haven't installed Tidyverse, okay, it would not have appeared here. But once you installed Tidyverse and then you go to packages and then type Tidyverse, it should appear here already. Now it's loading. Okay, there you go. It's done. So I have installed packages Tidyverse. I should not have done that anymore because if I when I went to packages, it's already installed. So no need for that. Okay, so even if Tidyverse is already been installed, you only install once unless you're updating. So if you have installed Tidyverse, then no need to reinstall it. But the functionalities of Tidyverse are not yet available. So there's one thing that you should do, and that is either use library Tidyverse. Notice that in install.packages, you put it in quotes. But if you use library, which is the same as, I'll comment this out, require Tidyverse. So either you can use library or require. Okay. So if I run this, I just want to run this line. I'll go here, anywhere here, even at the end of the comment. It will only run this specific line. Okay. Control enter. And then you can see here, class, that what happened when we installed that, when we library Tidyverse. You notice that there are some comments here. Package Tidyverse was built under R version 4.4.2. And then there are some packages that come preloaded with Tidyverse. So for example, dplyr is a package. Forecast, it's a package. ggplot2, it's also a package. Lubridator with our string art table Tidyverse, these are all separate packages. However, this has been placed into one, let's say, universe of packages called Tidyverse. So when you install Tidyverse, you also install these packages, okay? And then there's there's a note here about conflicts. It says here, okay, conflicts. Tidyverse conflicts, dplyr, the package dplyr, okay, conflicts with the stats package, okay. The function filter is the same for the filter in stats. So how will R know which to choose? Unless you specify that you need the stats package, okay, it will make use of the dplyr package, okay, for the function filter. Okay, so if you're using the filter function, then if you didn't identify whether it's a dplyr or stats package, then it will default to using the package dplyr. Okay, so it will mask the filter function of stats. Same thing with log. Okay, it will also mask stats package is also this function log. It will mask it and it will use dplyr. Okay. Okay, so now the function read underscore, and also what happened. Okay, let me just show you. What happened to Tidyverse when we run library? Okay, here. Library Tidyverse. Notice it became checked here. A while ago, that was not checked. So when your package is checked, okay, it means that it has been loaded. Okay, it means that you are now ready to make use of the with the functions coming from Tidyverse. If I if I type stats, you notice that stats is also loaded, but we did not use library for stats. When you open R Markdown, R Studio, then automatically stats package is already preloaded with it. So that's why we did not write the code library stats or require stats. Automatically, this is already preloaded. And take note, you cannot update it. For other packages, you can, okay, either remove, okay, or browse. Okay. For this one, stats and stats for, there's no provision for that. Well, you can also go here. Okay, so let's now go back to the code that we used a while ago. Let's go here first. Okay, let's go back here and create this object wage, and then use read underscore CSV, wage.csv, column names is equal to true. Let's run this. And what do you have there? Okay, so it tells us that the wage data set has 526 rows of 8 columns. Okay. There are 3 character variables, 5 double, which means these are numeric, and it takes on decimal places. Okay. All right. Did you get it, class? Kindly chat yes, please, if you got the wage data set. Okay, good. Good. Okay. So what did we learn there, class? You cannot use read underscore CSV unless you have loaded the package. Actually, class, where in what specific package did read underscore CSV comes from? So let's type double question mark and then read underscore CSV. Okay. Let's ask for let's run this, control enter. And then in the help function, I guess, there, class, there. Read underscore CSV. Where's that? Okay, inside dito. All right. So, hindi siya naglagay ng help. But it tells us that it came from the readr package. Okay? Readr package here, which was which was included when we loaded tidyverse. But a while ago, I said that when you load tidyverse, it also loads these other packages with it. So very convenient. Okay, so now we were able to read the wage data set. And also, take a look at your environment. Here, class. Environment is here. Okay, so it tells us that the wage data set has 526 observations and 8 variables. If you want to see that, as just like a spreadsheet here, you can make use of the function. You can click this or type view wage. Let's click this first. If I click this, class, this spreadsheet here, okay, clicking it is equivalent to writing view wage there. Okay? Dali lang, class, ha? Okay, sorry about that. So we can see here that this is the wage data set. Okay? This is the wage data set. And I just wanted to discuss with you something about the model. We go back to what we were discussing a while ago I just went ahead, way ahead of myself, and it's to discuss the okay, this one, homogeneity of residuals variance. So there's a mention here of residuals. Another mention is homoskedasticity. Okay, related to this is the term heteroskedasticity. So let's just quickly discuss that. Okay, so this is your data. Suppose we're going to create a model where we'd like to relate hourly wage with these all other factors here. Education, experience, tenure. Okay, so we will create a model where I'll annotate it here. Our hourly wage, y sub I, okay, is equal to a certain, an intercept plus, okay, beta 1 times education, which is x1. So let me just limit it just to 2, beta 2 times x sub 2. So we're just using education and experience in order to model hourly wage. All right. So how do you model this? Let's take a look at the first observation. Our actual or observed value, we call it observed value, is 3.10. Okay. So what we do is, so that's our observed value. Then once we have computed for beta null, beta 1, beta 2, what we do is to substitute the betas with x1 is, in this case, 11, and x2 is 2. Okay? So we know the value of, assuming that we have already computed for the linear regression model, we know the value of beta null, we know the value of beta 1, we know the value of beta 2, and then we substitute there your x1 and x2, which are 11 and 2. Now, once we get these values, okay, this one, the value that we get here is called your predicted value. That's your predicted value. Why is it called predicted value? Because it was derived by making use of the model and then generating the value. Okay. So let's say this is, let's suppose this is equal to 3.0, 3.00. So if we compare class the observed value, this is the actual value, and the predicted value, you notice that they're not the same. So your actual value, your observed value, y sub I, is usually not the same as your predicted value. So your predicted value is denoted by this one, there, hat. Okay, if you see your variable having a hat, it means that this is your predicted value. This was generated by predicting it using a particular model, in this case, a multiple linear regression model. Okay, so notice that they're not equal. Okay, y sub I, 3.10, is not equal to y y hat. Okay, now the difference between your actual value and your predicted value is called your residuals. Okay, residuals ang tawag doon. Okay, so this is our independent variable, right? Any model that we create, let's say we have created that model, we're going to compare it with the predicted value by using the values here. Whatever we get, we compare with our actual value, our observed value. Whatever we get, the difference between the two is your residual. So in order to make the y sub I and the y hat sub I, we will have to add the residual there, epsilon sub I. Okay? So that it becomes equal. Otherwise, it will not be equal unless they're perfectly equal. Okay? So this is your observed value, your actual value. It's equal to your predicted value plus your residual. Okay? In other words, your residual, epsilon sub I, is equal to your actual or observed value minus your predicted value. There. Okay, so that's your residual. Residual is equal to observed value minus your predicted value. Now, the our text says that the residuals, this one, the residuals should be what? Constant. Okay, it should be constant. How does that look like? Okay, so how does that look like, class? Let's say we plot we plot our okay. I think it's best to instead of me plotting, let's go to the okay. Let's go here. Okay, I provided you some references here. Okay, kindly copy this, class. Kindly copy this and open it. Okay, and then it will bring us to this one. Okay, this one. Okay, so let me explain to you what constant variance is as regards your residuals. Okay. So if you plot the residuals and then it behaves like this. So how is this behaving? This is our residuals, and notice it's not constant because as you increase your x value, your residuals keeps on increasing. You notice at this point the variance is at this area, at this point, the variance is only up to this point. At larger values of x, the variance is already, the variance of your data is already this one. Okay, and maybe if you keep on increasing it, it would be larger. So this is a situation of non-constant variance. Okay, this is also non-constant variance because if you increase the value of x, your variance becomes smaller. Small values of x, this is your variance. Okay, but larger values of x became smaller there. All right. So these two are instances of non-constant variance. Okay. On the other hand, this one, class, is constant variance here. You notice that even if you go to higher values of x, assuming it will still behave this way, then your variance is not increasing over time. This one, your variance is increasing over time. Not over time, sorry. Your variance is increasing over larger values of x. This one is your variance is decreasing. This one is constant. This is what we call homoscedastic residuals. These two are called heteroscedastic residuals. So when we use multiple linear regression, class, you have to look at your residuals. Okay, you have to analyze your residuals, and your residuals should be constant. If your residuals are not constant, then you're suffering from heteroscedasticity. And you don't want your residuals to be heteroscedastic. Okay? You don't want your residuals to be not constant. You want your residuals to be constant. Okay? So that's the third let's say condition for or assumptions in classical linear regression model. Going back here, this is it, class. Constant variance. Okay. Homogeneity of residual variance. Homoscedastic constant variance. Variation in the residuals or amount of error in the model is similar at each point across the model. Okay. So may I have again your chat, please? If it's clear so far. Clear plus so far yung yung homogeneity of residuals, the homoscedasticity. Okay, good. Thank you. We want the residuals to be constant. How are residuals generated? Residuals are generated after you have created the model. Okay. And then you have what we call the predicted value or computed value. You compare it with your observed value. The difference between your observed value and your predicted value is your residual. When you plot your residuals, it should behave in a constant manner. Your residual should not be fanning out. When I say fanning out, it's increasing over a larger value of your independent variable. And it should not be fanning in. Okay, yung kanina fan out going this way, fanning in, it's decreasing. All right. Thank you. Thank you. Good. Next, another condition is this one, class. Okay, they should not be collinear. Okay. Now, what's this, class? And how do we explain this? Let's see how this was explained in the notes that I provided you with. Okay, is it here? Okay. Here, class, number 5 here. You can, multicollinearity means, class, that, okay, let me start with this. We want your dependent variable and independent variable to be highly correlated. We want them to be, to display a high correlation. However, it should be with the dependent variable and independent variable. Now, we don't want that as far as the two independent variables are concerned. We don't want that x1 is highly correlated with x2. We don't want that because we will we will experience what we call multicollinearity. Okay? And if we have multicollinearity, that can be a problem because it will be very difficult to disentangle the effect of those two variables. Because the objective of multiple linear regression is to explain your dependent variable. And if your two independent variables are competing in order to explain your dependent variable, then we will have a problem. Because the objective is to determine how much of the variation of your dependent variable is being explained by your independent variable. How much is x1 explaining y? How much is x2 explaining y? So if x1 and x2 are very correlated, in fact, let's say they're perfectly correlated. Okay. What do you mean by perfectly correlated? X1, let's say, is equal to, let me just very crudely give an example. So this is your x1, this is your x2. Okay, x1 is 4, then 5, then a 3 here, then 2. So let's say these are your observations, then a 2. And this is equal to a 9. Okay, this is 11. Okay, this is 3, right? This is 10. And then this is 5. And then this is 5. Is there a problem with this? Yes, because x1 and x2 are perfectly correlated. How? x2 is derived by multiplying x1 by 2 and then adding 1. 4 times 2 plus 1. 5 times 2 plus 1, this one. 3 times 2, sorry, this should be 3 times 2 plus 1, 7. 2 times 2 plus 1, etc. So x1 and x2, x2 was derived from x1. And this means that they are perfectly correlated. Okay? They're perfectly correlated. So, in fact, if we plot x1 and x2, you'll have this. x1, x2. You'll have a perfect line. Say, like this. Okay? So that's perfect correlation. And we don't want that because that will create havoc to our model. So, remember that we don't want multicollinearity. So that's what that addresses. No multicollinearity here. Okay? Explanatory variables should not be collinear. Okay? Otherwise, it can be hard to disentangle which of them best explains any shared variance with the outcome variable. The objective is to explain the variation in your dependent variable. So when your dependent variable, if your x1 and x2 are perfectly collinear, then we don't know, it would be very difficult to split how x1 or how x2 uh, describes your dependent variable. All right, so no multicollinearity. When does that happen? If you take their correlation, it's very high. Okay? We don't want your independent variables to have high correlation. We want your dependent and independent to be highly correlated, but not your dependent variables. All right, this one, independence of residual error terms. All right, in order to understand this, let's first discuss the three types of general types of data. Number one, you have your cross-sectional, okay? Cross-sectional data. You also have your time series data. And thirdly, you have your panel data. Panel, sorry for the writing. Panel data. Okay, so what's the difference between them? Let's take a look at it in terms of units. Let's differentiate them in terms of units and then time, time period, time or period. Okay, so when you have a cross-sectional data, you're taking a look at many units, one time period. So for example, let's have a study of all the Asian countries, and then let's take a look at their, let's say, population growth rate, and then their GDP, GNP, etc. So you have this type of data where you have several countries, Asian countries, Afghanistan, Azerbaijan, Uzbekistan, Tajikistan, Central Asian countries, and then Mongolia, China, Japan, Korea, etc. All the Asian countries, including ASEAN. So we have those data, macroeconomic data, and all of this were taken only in 2024, 2023, one year. So if you have that class, you have several units, several individual countries. The units there is the countries, and then the time period there is the year 2024. Okay. So what type of data is that? Cross-sectional data. On the other hand, to distinguish that from the time series data, time series data takes a look only at one unit, one individual, and then several time frames. Okay, so how do we do this? Let's just take a look at the Philippine data. Philippines. Okay, so you only have one unit, Philippines, one individual. When you say unit, that's what's being observed. Okay, and then time frame many, from 1970 2000 to 2020 24. So what type of data is that? That's what you call a time series data. We're taking a look only at Philippines and then across several points in time. Okay. And lastly, you have panel data. Many. Okay. So that's what we call panel data. So it combines your cross-sectional and your time series data. So you have all the Asian countries. Sorry, all the Asian countries from 1970 to 2024. That's your panel data. And often panel data are more robust. Okay, among the three, okay, panel data are the most robust forms of data, type of data. And usually in your thesis, in later in your thesis, you do not usually use cross-sectional. You don't use time series data. You use panel data for your paper. Okay, because cross-sectional or time series data is a bit simpler than panel data. For thesis paper, medyo hindi yung depende din sa ano, no, but it's usually panel data. All right. So I hope these are clear. Now, what do you mean by independence of residual terms? Okay. So you know what residuals are, right? We know residuals. If we plot the residuals, okay, let's say this is our residuals. Let me plot red. And it turns out that your residuals behave this way. Okay. There's our residuals. You notice that there seems to be a pattern. There's a trend. It's increasing over time. Now, this is an example of an interdependent. Okay. There's a dependence in your residuals. Why? Your residual here is dependent on your previous residual. Your residual here is dependent on your previous residual. Okay. This residual is dependent on your previous residual. So there's dependence, interdependence of residuals, residual error terms. So if this is your residual, then you have a problem. The assumption of classical linear regression model is that the residual should be independent. In other words, if you plot it, there's no correlation, it's just a random pattern like this. Like the one that I showed you a while ago, di ba? Ito. Constant yung variance niya, hindi lang constant, ano pa? Walang correlation, no interdependence, no dependence among the residuals. Okay? Now, this independence of residuals is more we're not concerned with that as when we're dealing with cross-sectional data. Okay? So when you're doing regression and you're using cross-sectional data, this is not an issue. You know why, class? You know why? Because it depends on how you arrange your data. Suppose you arrange your data, let's say in Asian countries, no, alphabetically. And then, so you have your residuals, right? Each country will have their own residuals, and then you plot it. Now, the plot will be different if you rearrange the 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 arrangement of your data. Let's say it's randomized now; it's not alphabetical. So if you do that, then you'll have a different uh, sorry, you'll have a different plot of your residuals. Okay, so that's why I'm saying that independence of residual terms is not an issue with cross-sectional data because data here can be rearranged alphabetical, sorted from highest to lowest or lowest to highest, etc., or random. On the other hand, time series data has an inherent inherent arrangement of the data. It has to be chronological, 1970 to 2004. So you cannot put 2024 first. I'm sure 2024, I meant 2024 first, and then 2010, and then 1978, etc. You can't do that because time series data has an inherent structure that must be followed. Okay? So if your data is such that the residuals of let's say 2000 is affected by the residual of 1999, and so 1999 is affected by 1998, okay, then you'll have such a pattern. Okay, you'll have such a pattern. So this is more a problem of the independence of residuals, is more a problem of time series data, and it's also a problem of panel data, but not cross-sectional data. Okay, so that's what this means. All right, and lastly, you have normality of residuals. If you plot the residuals, they should be at least, at most, around about this one. Okay, normally distributed. Okay, but we will discuss what happens if these assumptions are violated. What is the remedy that we have to do? All right, so let me clear the drawings again, and may I also invite you to copy this class, and let's take a look at it here. Okay, by the way, there's a mention here, class, of blue. Okay, blue class. What's blue? Blue stands for best linear unbiased estimator. So if all the conditions, assumptions are met, then we have the model, the regression model to be what we call blue. Desirable, it's a desirable blue property, best linear unbiased estimator. Okay. All right. So here, this is another one. Okay, sorry. Multiple linear regression. This is the other site that I gave you. Okay, take a look at this. Here you're plotting, okay, you're plotting your Y, okay, removal, and your ID, your independent variable. Your removal and your ID are strongly correlated. So that's good. Compared to this one, removal and width. So we say that ID here is a better predictor because the relationship between because there's a higher correlation between removal and ID as compared to this one. Okay, removal versus width. All right. If this were independent variables class, granted for assuming for the for discussion purposes, let's assume that these are both independent variables. Okay, then we might have problems with removal and ID, but not so much with removal and width. If removal was an independent variable, ID and width also independent variable, then removal and width will be better to be inside in the model as compared to removal and ID because removal and ID are highly correlated. Okay. All right. This is the equation I said a while ago. Your Y. Okay. This is your predicted value. This is your Y hat. Y is equal to Y hat plus your epsilon. Okay. This is simple linear regression. This one. This is multiple linear regression. We have two parameters. Okay. This is also multiple linear regression with P predictors. Okay. Now this is what I mentioned a while ago. This is okay. Linear regression models can include functions of the predictors of x's like transformations, polynomial terms, cross products, just like this. So x can be square root. X can be transformed into a logarithm. X can be squared. X can be an interaction between x1 and x2. Okay, but not beta. You cannot square beta. You cannot exponentiate beta. Okay, you cannot multiply beta 2 and beta 1. You cannot do that. Okay, so that's what I meant a while ago. Okay, going back now to our discussion. All right. So this one class tells us that your epsilon, this is your residual, is equal to your actual value, your observed value, minus your predicted value. Remember, class, hat, when you use this in LaTeX, this will actually print a hat sign in Y. Okay? So the residual is equal to the observed value minus the predicted value. Okay? And what happens when you add up all the residuals, class? When you add up all the residuals, this is what will happen, class. Sum of all the residuals is equal to, it's always 0. Okay? So you have your model, and then you you compute for the residuals. Some will be negative, okay? Negative because the predicted value will be greater than your observed value. Some will be positive, where the predicted value will be higher than where the observed value will be higher than your predicted value. Okay, so when you sum up all the residuals, okay, the answer will be 0. Let me go back here just to show to you where is that in our model here, in the first one here. This one class. How is that presented here, class? Okay. Conditional mean should be equal to 0. Okay, what does this mean? If you get the average class of the residuals, it will be equal to 0. How do you know that? Because the sum of the residuals is equal to 0. Okay, remember, how do you get the mean? To get the mean of a number, okay, obviously, the mean of a number is equal to the summation. Okay, in this case, we're summing up your residuals and then divide it by n, right? This is the this is the mean, E hat, E bar of your residuals. Sum of your residuals divided by n. And since this is equal to 0, divided by n still equal to 0. So here, class, the conditional mean should be 0, or mathematically, the expected value of your epsilon given x is equal to 0, or just expected value of your epsilon is equal to 0. So don't be intimidated by this. It just tells you that the average of your residuals is 0, born out of the fact that when you add up all the residuals, they're all equal to 0. So what's the importance of that? If the assumption is that the mean of the residuals is equal to 0, then that means, class, that you cannot use you cannot use the mean for you cannot use that to in order to generate your regression model. You cannot use this summation of your residuals, epsilon, okay? Because this is equal to 0, okay, you cannot use this in order to compute your regression line. However, what you do is you square the residuals, okay? Definitely, this will not be 0 because the positive residuals will become, they will all become net positive, and then you sum that up, okay? And then how is the regression model determined? Okay, the regression model, class, so suppose we have this one. Let's take a look at, back to our, sorry, back here, just here, class. So our regression line, this one here. Let me just, okay, let me delete that. Okay. Okay. Where's here? Okay. So this is the regression line. Now the regression line, class, is a unique line. Given these points, given this relationship between your y and your x, there is no other regression line except this line. Okay. You will not find any other regression line okay, given removal and ID except this one. This one cannot be, class. This one cannot be. Okay, why? Why is that so? Because the regression line is computed in such a way that, okay, how is that computed? So we go here. So this is your observed value. This is your predicted value. All the predicted values are in your regression line. So this, class, is your residual. The difference between your observed value and your predicted value is your residual. Okay, this is also, so some residuals are low, some are very big, okay? Some are, so this is your, if your observed value is below your predicted, that's negative. If your observed value is above your predicted value, that's positive. Okay, so how do you determine this line? This line is determined by using a little calculus, okay? And what we use is not the squared of the residuals. I said not the sum of the residuals. You square it first, okay? You square it first. So here is the residual, and then we square it. If you know, class, squaring it is simply getting the area, okay? Square, square, okay? So get the square, this is your residual, get the square, get the square of everything, and then sum that up. And what is the characteristic of the regression line. The regression line is such that the sum of your residuals is a minimum. Minimum. Okay? Minimum. If you compare, if this was your regression line, assuming, and then you compute for the residual squared, it will have a higher residual squared compared to this one. So this one, this blue line, is the only line that gives you the minimum, the smallest sum of the residuals squared. You will not have any other line. You cannot find any other line, okay, that has the characteristic of having the the lowest squared residuals. Okay, so let me just end something here. Okay, going back to our lesson. Okay, properties class. It's almost time, so I hope you give me a few just a few seconds. Number one, the regression line passes through the center. What does that mean, class? Quickly, if this is your model, this is your y, this is your x, this is your y bar, average y, this is your x bar, average x. Okay, this is the point of x bar, y bar. Always the regression line will pass through that there. Okay, it will always pass through the center of gravity. That's what this means. Okay, pass through the center of mass point. Secondly, the sign, okay, the sign of your slope of your regression line, this is your beta 1 plus. This is the slope for x1 plus. The slope is equal to the sign of the correlation. Obviously, class, the correlation here is positive. Okay, the slope will also be positive. And also, we mentioned here, class, the sum of the residuals is 0. Okay, or the mean, conditional mean of the residuals is 0. Okay, so next meeting, we're going to already start with using the wage data set. Okay, so kindly learn how to install packages, because we're going to learn. Please review, please try to see what Pacman is. This is a package also. You have to install this first. And please learn what the payload function is. So next meeting, we'll quickly go through that. I expect you to know that already. And then we go to the next part of we'll go now to the formal regression modeling. All right? So thank you so much. I'll stop recording now.